Okay, so what I want to do real quick is actually branch into non-determinism. Now, I've mentioned this a few times when deferring to NFAs when I bring up some finite automata. And that is because everything we covered so far, as I've stated several times, is DFAs, so deterministic finite automata. But now we're going to move into the non-determinism branch of our computational models. So without further ado, let's take a look at the slides. Again, this is just basic non-determinism. I will cover some NFA material, but I will cover more specific NFA material in the next video. So take a look at some of their differences. Now, determinism in this concept is going to be every step of a computation follows in a unique way from the preceding step. That is the defining characteristic of a deterministic finite automata, so the DFA. Every state has exactly one exiting transition for each symbol in the alphabet, so their nature is quite strict and comprehensive. On the other hand, non-deterministic finite automata, primary difference here is the fact they do not need a single transition at every state and step in the machine. They can choose to have multiple of that same transition at a state, or none at all. So several choices may exist for the next state at any given point in the machine. That's that first part. Multiple can exist in one state, but also since none can, it just depends. Now, every DFA is considered to be an NFA since non-determinism is a generalization of determinism. It does not work the other way around. There are going to be things about NFAs, and if you try to say, oh, this is also DFA, it fundamentally would just not work. It's very similar to all squares are rectangles, but not all rectangles are squares ideology right there. So, the best thing about NFAs is they are extremely flexible. So if we look at the following one, you can see that it looks quite similar to the previous DFAs that we've covered, and it's got a state diagram, there are transitions going on, you've got different states, a start state, accepting state over here. It looks pretty familiar. However, there are definitely some key differences here that should be fairly apparent right now. That being, this should look a bit weird. This is definitely new, and a few more subtle ones. So let's take a look at those. So the first one of these differences is the fact that Q1 contains two transitions using an input of 1. There's a 1 here in the loop, but there's also one going to Q2. And again, in a DFA, this would not work. We need unique transitions. This is not unique. This means that this 1 can take multiple branches. So that's exactly what it's going to do. It'll split off and diverge into non-deterministic paths. Next is we have that symbol here, epsilon transition. That is an empty string. So essentially, this allows us to make a transition from one state to another without actually parsing an input. We can use that later on to combine multiple FSMs into one. We'll talk more about that with the regular operations we covered in the previous video, but for right now, what this means, instead of doing this 1, 0, 1 approach that DFA would require, this, we can now choose 1, epsilon 1, which will reduce down to just a 1, 1, because this is basically a free move from Q2 to Q3 without really having to actually parse anything. And those are very, very nice to have. Beyond that, we can also have states that do not contain a transition of a particular input. So Q3 here does not have any input for anything but 1. There's no epsilon transition, there's no 0 transition, it just doesn't have one. So essentially it means that that current branch in our non-deterministic branch would be dead. And it kind of looks a bit like this being our DFA approach, exceedingly linear, very strict in nature, very comprehensive, and then we get this cacophony over here, this diverging tree that is just cascading down into oblivion and a lot. So many reject states over here, a lot of things going on, eventually down to this accept. So this is the primary difference. This is the flexible nature. There's so many different paths you can take, and it's honestly quite wild. So DFAs, they're very linear, very straightforward, where NFAs kind of have the ability to guess the correct path by making multiple branches, essentially. So on the previous one, we had multiple ones at a particular point, Q1, and you would go down two different paths, and you would just continue on until maybe you got to a state that rejected, or you got to an input that just did not have what you were looking for, and that branch halts there, essentially. We can actually look at it by looking at that previous NFA that we're looking at, Q1, Q2, Q3, Q4. We can try and parse this string of 0, 1, 0, 1, 1, 0. Now, looking at this, not this on the right, just on the left side, we would see that I have a loop here on 0, and I can see that I can take a 1 here, but I'm essentially just never going to live Q1 if I do this. Logically, I can see I'm going to do a 0 here because it accepts. I'll do a 1 transition here. I can do a 0 transition here, a 1 here, a 1 here, and a 0 here. I can take that logical approach just by analyzing my states in front of me, and I can make that decision. Like, I can do that. That's perfectly fine because I can see the entire thing in front of me. Computers didn't always do that. They had to process these strings one thing at a time. So you end up with something much more complex looking and honestly way overcomplicated than what we would perceive this as. So let's walk this through to see what the actual machine is looking at. So our start state is Q1, yeah, that's good. I'm going to take this 0 input. It only has one option, it goes to Q1. It loops on itself. So that's exactly what we would do. We just go here. But now you see it split off to 3 points. And it might make sense because, you know, Q1 is going to loop to itself. That's fine. We have this branch right here. And then Q2 is going to move on. And that's this branch right here. What is happening here? Why does this exist? Well, this exists because Q1 on a 1 input jumps to Q2, but Q2 on an epsilon input jumps to Q3. So technically Q1 can jump directly to Q3 just by doing 1 epsilon, which is still just 1. Because anytime we have an epsilon, that's an empty string, and it just goes away. So that's where this branch is coming from. We're just saying instead of going to Q, because we're not reading in epsilon. You don't read in epsilon, essentially. You can just reduce them down. So we have Q1, Q2, Q3 trajection, or trajectory. The Q3 path, it's going to halt immediately because the next state is a 0, essentially. And as we said, there is no 0 input on Q3, so it's out of the question now. But Q1 can do 0, and it can just go straight here to Q1, just like it did back here. Q2, however, moves on to Q3. So that's where we are, and now we're reading a 1. Again, Q1 can go to all these places. And if you notice, Q2 does not have a 1 input, so it basically is done here. I'll come to the side in a second. Q1 goes to 1 on itself. That's perfectly fine. It can always loop back to itself on any input. So you're going to see this Q1 path diverging over here to the left, and eventually it'll just halt on its own. This one's a bit more interesting. We'll touch that in just a second. So back over here, we're still reading that 1 input. Q3 goes directly to Q4. And technically we could accept there if we wanted to, but we still have input, so it's just going to loop anything. So the 1 comes in, 0 comes in, and we accept here. So that was essentially the path that I took earlier, this 0, 1, 0, 1, 1, 0. That's exactly the path that I took here. That's not the only option, though, as evidenced by this path here. Maybe you saw this one, took this path. We can already basically say, yeah, anything that's going to loop on Q1 eternally is just not going to work here. And if we did this Q1 path to Q2 here, it would eventually get to it, but it's run out, so it's not going to make it. And there's no zero input here. So those are all end of lines. But let's take a look at this other path, the one that I didn't mention earlier. That's Q1, 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 Q3, Q4, Q4. What is going on here? So let's follow that through. So we have 0, 1, 0, and then it does this. It does the 1 epsilon to get to 3, 1, and then 0. So it kind of uses this as to its advantage. And so we have two different branches that we can take to get an accepting string. So the one that's very, very obvious, which is the whole 0, 1, 0, 1, 1, 0. That is very much a DFA-centric approach where we just are progressing at every single point that we would really want to. That's that deterministic path that we want to try to take. And the NFA approach is saying, like, hey, I can do this 1 epsilon approach and just skip to 1 to 3, stay here the whole time, guess this is the point that I need to come out, get to 3, get to 1, and then just loop here until you're done. And that's exactly what it does. It just loops 1 here over and over and over again until it knows, hey, I can get from here to go to Q3, go to Q4, Q4, and we're good. Because that is an actual option that it has, thanks to this epsilon transition. So this is the whole non-deterministic idea here, is that there's not just one path, there's multiple paths that we can take. And as long as you can get one path that works, that's perfectly fine. If you can get multiple ones, that's, I guess, better. It might be more flexible in the future if you can like open up more paths by adding some epsilon transitions like this one. And it genuinely does provide a much more flexible approach to this computational process. Now, that epsilon transition adds so much versatility. Now, in this case, this is actually the example of doing a union of two separate machines. So we can look at here. That's awful, but eh. And here, those are two separate NFAs. Actually, we can say that those are two separate DFAs as well. Wouldn't change any. Well, actually, no. Since, well, no, it's only a unary input. It's just a zero alphabet, essentially. These are in DFAs, NFAs, it doesn't matter. At the end of the day, it's going to be an NFA because we have these epsilon transitions. Because what we're doing here is, let's say that I call this N1, this is N2. I'm saying this, N1 unioned with N2. I do that by using these epsilons because I can start here and then epsilon transition here, which is an empty string which would not change this N1 at all. I parse the same exact string because this didn't affect anything on what I actually read as an input. Same thing here. I just choose which one of these I want at my own whim. And so what this gives us is an NFA that accepts all strings of the form 0k, where k is a multiple of 2 or 3, superscript denoting repetition rather than exponentiation. So this needs 2 zeros to actually accept, or this needs 3 zeros to accept. So 0, 0 would accept right here. No zeros would accept on either one of these because it's just an empty string transition to an empty string. 3, that would accept right here. 4 would accept here. 5 wouldn't accept at all. 6 would on either one of these. So just a multiple. But this is a whole union process that this versatility from epsilon allows us to apply our regular operations. No problem. So again, this is a bit more of a straightforward approach on it. This is trying to get n equals n1 union n2. So we can union the NFAs by creating a start state that epsilon transitions to their respective start states. So n1's original start state is here, n2's is here. Ignore everything else, it's not very important right now. In the overall set that we want, N, then we create this start state here, separate from these, and then I'll epsilon transition to this one's start state, and then epsilon transition to this one's start state. And then I can choose whichever one of these that I want. And that's exactly how union works. Meanwhile, concatenation side is a little bit more of a linear approach, where now instead of choosing one of these two, I need to lead N1 into N2. So that's what I'm getting is N equals N1, N2. And so we concatenate the NFAs by epsilon transitioning from the accept states of N1 to the start state of N2. So we're going to start in the same place of N1. This is our actual starting state for N. But instead of accepting here on these three, I'm instead going to epsilon transition all three of them to this start state in N2. And then I will keep these in my accept states. So that's just kind of bridging this gap right here, just like so. And that's concatenation. And finally, we have a star operation. And this one's a little bit more complex. So star operation is any repetition of our NFA. So in this case, we have N1, and so N1 star is N in this case. So I have any number of these, and that does include the empty string. So what we want to do is to create a new start state external to the original one. So we have N1 here, which is now populated right here, but then I make this empty state of my own, because if I want 0 repetitions, it just needs to halt directly right here. Then if I want 1 repetition, I epsilon transition into my actual start, and then I begin the process. And I keep my accept states the same. But then I will epsilon transition back to my start state. So now if I do this, I have 0 repetitions, halt here. 1 repetition, go to my start, do my whole process, and halt at my accepts here. 2 would be to get here, transition back to the start, repeat my process, and halt. 3 would just be continue this on, and so I can kind of loop this back and forth over and over again. And that is essentially going to be all the regular operations that we can do with NFAs and our basic non-deterministic approach. So I hope all of that made sense. Again, this isn't getting too much of a deep dive into NFAs themselves. It's more behind the idea of non-determinism and getting those non-deterministic paths down. Also, there's a reason we're going to say NFAs and DFAs a lot. It gets hard saying non-deterministic like 15 times in a row, but I digress. So I do hope all this made sense. I hope it was helpful. Hope you learned something, and I'll see you in the next video.